We'll now start on the final part of section 3.2. We're just actually kind of putting some things together here and talking about regression wisdom and correlation wisdom, and also how to find the slope of the least squares regression line given just the means and standard deviations of x and y and their correlation. Let's start by looking at interpreting computer regression output. Many times in AP Stats, rather than asking you to enter a large set of data into your calculator, you'll be given a computer output and asked to just read that computer output. Here you can see computer output for the Ford F-150 trucks that was done using Minitab, which is just a computer program for statistics. So how do I get the equation of the least squares regression line? It's y hat equals. Here I'll have the y-intercept. This is the coefficient of the constant. And remember, in a y equals a plus bx, the constant is your y-intercept. So 38,257 is your y-intercept. Plus, and then if you'll recall, miles driven was your independent variable, your explanatory variable, your x. So the coefficient of x is your slope. You can also see the value of S given here, which is 5,740.13. This is the standard deviation of the residuals. And then R squared is 0.664. I normally write that as a decimal instead of as a percent, but it doesn't matter either way. You'll never use the R square adjusted, so just ignore that. And then all these other numbers in the regression output are not important to us now, but they will be later on, so just hang on for next semester. Regression to the mean is just asking us to calculate the least squares regression line given the means and the standard deviations of both x and y and the correlation between the variables. And so what you need to know is how to get the equation of your least squares regression line given the slope, or to be able to, an equation for the slope, and an equation for the y-intercept. These are both on your formula sheet, so you don't have to remember that. A really important point, though, that you do need to know is that the y-intercept, this little formula for the y-intercept, comes from the fact that the least squares regression line always passes through x bar, y bar. In other words, if we found the means of the x's and the means of the y's, and wrote that as an ordered pair, the least squares regression line always goes through that point. So here's an example. Let's use the means and standard deviations for x and y and the correlation between foot length and height, and this was collected from 15 high school students. So how would I get the slope? Well, it's the correlation, so 0.697. times the standard deviation of y, which is 10.69, over the standard deviation of x, which is 2.71. And if you calculate that, it comes out to 2.75. Now, I typically don't use that little formula they give me for the y-intercept, just because I know that what I have now is y hat equals a, the y-intercept, plus 2.75x. And now I know that the line contains the point x bar, y bar, so I just plug in the y bar for y hat and set that equal to 2.7a plus 2.75 times the x bar. Let me see if I can erase that where I put a decimal in the wrong spot. There we go. And then if you solve this for A, you'll get 103.34, which will make my equation y hat equals 103.34 plus 2.75x. And the last thing that we need to talk about is correlation and regression wisdom. So here are just a few things that you'll need to pay attention to. If we switch the explanatory and response variables, notice that the R squared doesn't change. That also means that r doesn't change because it's just the square root of the r squared. But notice that the standard deviations of the residuals as well as the least squares regression lines do change. So it's important to just know which variable is explanatory and which is response. We've already talked about this. Correlation and regression lines describe linear relationships only. So when I look at a value of r, it's telling me how strongly linear the relationship is. It never tells me anything about curved relationships. I think it makes sense that correlation and least squares regression lines are not resistant. One thing that's really important to notice, though, here we have least squares regression lines for age at first words and some kind of IQ score, I think. Look at child 19. Child 19 is an outlier in the y direction. If we take out child 19, though, notice that there's not much change between the correlations for the two regression lines or the regression lines. They change a little, but not much. Look at child 18, though. Child 18 is an outlier in the x direction. So this child was much older. And look at the regression equation when I take child 18 out. It actually made a lot of change. And what happened there, see if you can kind of picture this if I take him out. Child 18 actually strengthened that relationship, right? So if I take him out, the rest of these points are much more scattered. So child 18 is called influential. And you can see that in the next slide. This slide just talks about what outliers are, and they can happen in the x direction or the y direction. But lots of times the ones in the x direction are more influential than ones in the y direction, simply because they pull the regression line towards them. And then the very last thing, and this is important, association does not imply causation. So just because we have a high correlation between two variables does not mean that one causes the other. A study was done, a serious one, where it looked at the number of cars that people had and how long they lived, and it found that people with more cars tended to live longer. But does that mean if you buy more cars you'll live longer? Of course not. It just means that they were using number of cars as a quick indicator of wealth, and people who are more well off tend to have more cars, and they do tend to live longer, but it's not because of the cars, it's because they also have better access to health care and education and lots of other things that will make them live longer, and it's not the cars. So be careful with looking at a positive or some strong association or correlation and thinking that one thing causes another.